Those of you who were at EuroLLVM 2012 will have possibly seen Anton Korobeynikov demonstrate how to bring up a complete LLVM compiler for OpenRISC in 24 hours. I'm interested in how we get from there to a commercially deployable toolchain as quickly as possible. We'll need to be able to handle any code a compiler a customer can throw at us, and we'll need things like an assembler, a disassembler, linker, libraries, a debugger, and some utilities. Now, this talk concerns one common type of customer, the mid-sized electronics design house developing its own specialist chips with its own in-house DSP. Originally, this company would have added a small programmable element to its chips, and this tiny DSP was a great success, and the designer on his own would also write the assembly code needed. In time, this became a more powerful DSP version 2, which was even more successful, and now we have a small assembly language programming department. Today's DSP version 3 is even more successful, with a large set of assembly programmers implementing standard codecs. These codecs all come with reference C implementations, and so the company would rather program the DSP in C. Programming in C should greatly increase programmer productivity generally. But to justify this change, this small company must be able to deploy a compiler that is commercially robust, but not cost too much. In this case, the compiler development is simplified because the customer is only using a small subset of C, typically needs minimal library support, and has a single small user base in-house. Completing the generation of real instructions for table gen is a routine task for an experienced compiler engineer. With a simple architecture, LLVM instruction selection and register allocation are very simple and straightforward, and a working compiler with all the instructions can be achieved in a few weeks. The customer already has an assembler by definition, and usually that acts as a rudimentary linker. Libraries aren't that important, so we can use reference C implementations, and a minimal debugger just needs to be able to allow programs to be loaded and run on the target. And this proof of concept complete toolchain can usually be completed within 60 engineer days and allow the customer to see that things are going to work. We then need to ensure that all the required functionality is covered by LLVM. So that means making sure we've got an ELF assembler and linker. CGen can help generate an assembler, and porting an ELF linker is fairly trivial. Special functionality invariably found in these processors, like saturating arithmetic, we just support with built-in functions. And we get to where we can pretty much cover the whole of C in about 60 days. Then this boring part of plowing through testing, regression test cases, and improving optimization. And for a small, well-defined use case like this, 60 days is probably enough for a skilled engineer to deal with that. And finally, and this is perhaps a surprising one, even for a small user base, deployment takes just as long as the testing. And the reason is that a customer base that's used to a simple assembler can really get out of control when you give them a globally optimizing compiler, a debugger that can handle source level optimized code, and that can run linker scripts that can get you incomplete messes. So we've actually found we spend as much time there as in any other part of the thing. Only then does the customer realize the savings made by moving to C programming, and they've got a commercially robust LLVM compiler toolchain for their uses, and it's been achieved commercially in about 1 engineer year. I've rushed through this to give you the big picture. We've got a poster outside with all the gory details of how LLVM helped and the actual use case example on which this talk is based. So do come and talk to me and my colleagues later on today. Thank you.
Thank you.